Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Basavakalyan. In the 49th session of Graph Theory 2, we will discuss kinds of digraphs. Already we have discussed different types of subdigraphs, but in this session we will see what are the different types, or you can say kinds of digraphs. Okay. Now we will see simple digraphs. What's the difference between those graphs? We will see one by one. Simple digraphs. What is the simple digraph? A digraph that has no self loop or parallel edges is called a simple digraph. There also, in case of simple graphs, or you can say graph without multiple edges, loops, so that graph was considered as a simple graph. Here also, a digraph that has no self loop or parallel edges is called a simple digraph. So you have to keep in your mind, a digraph, of course directions are there. A digraph that has no self loop or parallel edges is called a simple digraph. So you can see this example. Here there is no loop or even no parallel edges. Parallel edges means between two vertices there are two different arcs in the same direction. Okay, there is no any such or there is no such edges in this graph. So no loops, no parallel edges. So such a digraph is called a simple digraph. What do you mean by asymmetric digraphs? Digraphs that have at most one directed edge between a pair of vertices. Digraphs that have at most one directed edge between a pair of vertices but are allowed to have self loops are called asymmetric, or you can say anti-symmetric. Did you get the idea? So this is an example. So you can see there are loops. Loops are allowed. Loops are allowed. But between two pair of vertices, if you consider between two pair of vertices, what you can say? An edge between a pair of vertices. Edge. Or you can say directed edge. Here simply we won't say edge. A directed edge is there between every pair of vertices. You can consider any pair of vertices. Is there any such edge? So one directed edge between a pair of vertices, not every pair, a pair of vertices, okay, are allowed to have self loops are called antisymmetric, or you can say asymmetric digraphs. Okay, so there are some loops, and if you consider these are the two vertices, yes, there is an edge between these two vertices. If you consider these two, yes, there is an edge between a pair. Between a pair, it is not compulsory like complete graphs. Every pair of vertices are adjacent. It is not like that. It is not like that. Okay. Between a pair, which pair you are considering, it is left to you. Okay. Between a pair, okay, there must be a directed edge. So digraphs that have at most one directed edge, one directed edge, that is very important. So between a pair of vertices there must be at most one directed edge and are allowed to have self loops. It implies multiple edges are not allowed in this graph, but self loops are allowed. So don't get confused with the complete graph in case of the undirected graphs. If I say pair, it implies every pair of vertices must be adjacent like that. So it will be a complete graph. Don't get confused with that idea. So what I'm going to say, digraphs that have at most one directed edge, it implies maximum one edge between a pair of vertices. Maximum one edge between a pair of vertices. What it implies? It implies there should not be any multiple edges or parallel edges between a pair of vertices, but loops are allowed. Then that kind of digraph is called asymmetric digraph, or you can say anti-symmetric. This is an example of asymmetric digraph. Okay, so don't get confused with the ideas. Symmetric digraphs. What do you mean by symmetric digraphs? digraphs in which for every edge AB, suppose there is an edge AB, there is also an edge BA. It implies if there is an edge AB, there is also an edge BA. So A to B, B to A. It implies multiple edges are allowed. Very easily you can understand this. Between two vertices, there will be multiple edges. One is from A to B, another one is from B to A direction. Okay. So such a graph is called a symmetric digraphs. Okay, no need to give any specific example. It's very easy to understand. Okay, A to B, one edge is there. B to A, another edge is there. Incident out, incident into. Similarly, incident out, incident into. Okay, so therefore, such a digraph is called a symmetric digraph. Let us consider complete digraphs. What do you mean by complete digraphs? Again, in complete digraph also we have got two different types: complete symmetric digraphs, complete asymmetric digraphs. There we have got only one graph, that is complete graph. But here, complete symmetric digraphs, complete asymmetric digraphs. What is the difference between these two? Let us consider. Complete symmetric digraph is a simple digraph. Complete symmetric digraph is a simple digraph in which there is exactly one edge directed from every vertex to every other vertex. That's the difference. Okay. A complete symmetric digraph is a simple digraph in which there is exactly one edge directed from every vertex to every other vertex. Like between every pair of vertices there is an edge, we used to say there. Here, if you consider any pair of vertices, there is exactly one edge. Okay, exactly one edge. So that will be the complete symmetric digraph. Okay, directed from every vertex to other vertex. Then what is the difference between the complete asymmetric digraphs? Complete asymmetric digraph is an asymmetric digraph in which there is exactly one edge between every pair of vertices. So that is the difference. So complete asymmetric digraph is an asymmetric digraph in which there is exactly one edge between every pair of vertices. Okay, so these are the slight difference between these two complete digraphs. Okay, a complete asymmetric digraph of n vertices, if you consider, then that digraph contains n into n minus 1 divided by 2 edges, that is nc2 edges, where we used to have the number of edges in a complete graph with p vertices is pc2. Like that, a complete asymmetric digraph of n vertices contains nc2 edges. But a complete symmetric digraph of n vertices contains n into n minus 1 edges. It implies 2 times as that of the asymmetric digraph, complete asymmetric digraph. So a complete asymmetric digraph is also called a tournament or a complete tournament. So what is that, we will see in detail later on. Okay, so these are the two complete digraphs. Okay, that is the difference between asymmetric and symmetric. We will see what is the balanced digraph. Balanced digraph. A digraph is said to be balanced if for every vertex vi the in degree equals the out degree. In degree must be equal to out degree, that is d plus vi must be equal to d minus vi. What is d plus vi and what is d minus vi? That already we know, incident out and incident into. Okay, so how many edges are incident out? That will be out degree of a vertex. How many incident are in incident into? That will be in degree of a vertex. So here if the incident out degree and incident into degree of a vertex, if it is same, so a digraph is said to be balanced if for it should be for every vertex. It should be for every vertex vi. So then such a digraph is called a balanced digraph. Okay. Now, so we will see the concepts walk, path and cycle. Already there also we have studied walk, path, cycle. Walk, it is an alternating sequence of vertices and edges. There we have studied. Here also in the same fashion we used to define walk, path and cycle. Okay, so that's why the idea of graph theory, which we have studied up to 3 units, is very essential. Without the knowledge of that we cannot understand even digraphs also. But the ideas of digraphs are little bit different. Okay, so the concept of walk, path and cycle are taken from undirected graphs, except that the directions of arcs must agree with the direction of the walk. That's very important. Okay, so the directed walk, if I say W equal to, as I said, it is an alternating sequence of vertices and edges. Okay, if I say W is equal to V0, E1, V1, E2, V2 and so on and so forth, En, Vn, where the arc EI belongs, or what you can say, the arc EI begins at Vi minus 1 and ends at Vi. The arc EI begins at Vi minus 1 and ends at Vi. Similarly, the length of a walk, as there, the length of a walk is nothing but the number of occurrences of edges in case of undirected graphs. Here, the length of a walk is the number of the edges that occur in it, similar to the undirected graph. So, a closed walk has the same initial and final vertices or the points. Closed walk. So it is a closed walk. Starting point and ending point must be same. Then such a walk is called a closed walk. So ideas are almost similar to as that of the undirected graphs. The spanning walk, spanning subgraph. If you recall the spanning subgraph of a graph G, spanning subgraph of a graph G is a graph whose vertex set is same as that of the graph G. It implies vertex set is same for the graph and the subgraph. It just may not be. So that is called the spanning subgraph. Here also the spanning walk contains all the points, or you can say vertices. Okay. The semi-walk. What is the semi-walk? The semi-walk in a directed graph is a walk in the corresponding undirected graph, and it is not a directed walk. That is the difference. Semi-walk in a directed graph is a walk in the corresponding undirected graph, and it is not a directed walk. So such a walk is called a semi-walk. Now we will see the concept of an underlying graph of a directed graph. So underlying graph, in case of planar graphs, already we have discussed what is an underlying graph. What we did there, the multiple edges are deleted, and instead of multiple edges only one edge is considered. So if between two vertices, if there are two or more edges, such edges are called multiple edges. Then instead of multiple edges only one edge is considered, and all loops are deleted there. So whatever the graph we got, that graph is considered as underlying graph. Same idea here also we have considered. So what is the idea of an underlying graph of a directed graph? The underlying graph G, underlying graph G of a directed graph D. So the vertex set of the directed graph is V and the edge set of the directed graph is A. Okay, suppose the vertex set of the directed graph is V and the edge set is A. Then the vertex set of the underlying graph, it will be the same as that of the digraph D. Vertex set is same. So the underlying graph G has same vertex set as the vertex set of the digraph D, and the edge set E is equal to that. There will be a difference. Okay, it is the set of the pair, or you can say the pair of vertices U comma V, such that UV is an edge of A. Okay, so that's the pair of vertices represents an edge. Instead of multiple edges, multiple, you can say the directed edges, we are considering only one edge. Okay, so what is the difference? The underlying graph G of a directed graph D, whose vertex set is V and edge set E, has the vertex set same as that of the digraph D, that is the set V, and the edge set E is equal to the set of the ordered pairs of the elements of elements of V, that is U comma V belongs to the edge set of D. Okay, so for example, here we have considered one directed graph and its underlying graph. See, you can see the difference. So there are two multiple edges between these two vertices. Instead of that, we have considered only one edge. Okay, again here also two multiple edges are there. Here we have considered only one edge. So this is the underlying graph of this digraph. Okay, so these are the ideas. So far in this session, what we have discussed, so simple digraph, that is without the multiple directed edges and loops, so simple digraphs, asymmetric digraphs, symmetric digraphs, and also we have discussed about the complete digraphs. Again, in case of complete digraph, there are two types. One is complete asymmetric digraph, another one is complete symmetric digraph. Then we have discussed about the balanced digraph, in which the outer degree of a vertex is equal to the inner degree of a vertex. Okay, then we have discussed about the walk, path and cycle. The concepts are similar to as that of the undirected graph. Then we have discussed the underlying graph of a directed graph. So these are the books for your reference. Already I have mentioned these in the previous session also. So with this we conclude this session. Thank you.